Hello again. Make sure everything's working. Speaker. So we're all good. Okay. So real quick, I said I would send out some stuff, but I thought maybe it'd be better to explain in person, maybe. So, well, video in person, kind of same thing. Um, so again, what I'm going to do is share my screen. You'd think after 4 years of COVID and online that we'd be better using these online apps, but they're still kind of. So I'm just going to share my window. There we go. Share. And here we go. So what I'm going to pull up is this. This is a website that I've used for years. And actually, I've communicated quite a bit with Dr. Laird. He's a very nice guy. We published a paper on our blood pressure data we've collected over the last 10 years. And we did what's called a meta-analysis, which involves taking all the other papers published in that area, analyzing all their data, combining it with our data, and publishing it as one complete body of work. So you can see basically comparisons of all the research that exists for that topic. So anyway, I used this quite a bit for that. I had no idea how to do a meta-analysis. So I'm going to log in. This is actually, I think it's like $10 a year or something like that. So if you're going to, even if you're not using SPSS, it's actually a pretty good guide for doing statistics in other programs. I mean, it is designed specifically for SPSS, but so yeah, if I extend my membership, let's see, it's gone up a little bit, but 1 year's access, $19. So that's 3 years. That's really pretty cheap. So anyway, if you're doing stuff like that, it is quite useful. So updated graphs to version. So okay. So one cool thing is statistical test selector. This will actually, if you're designing your research or you're not exactly sure the data you've collected, what tests to do with it, this will help you. So if I'm looking for, like we've been doing in class, group differences, click that, continue. Okay. What type of study design do you have? So between subjects, within subjects, or between and within. And if you're not sure, here, look at a group, male doctors, female doctors, nicotine patches, hypnotherapy, or within, you're taking the subjects and treating all of them to the same things. So in a lot of ways, within subjects is better because you're controlling for the subjects. You're testing the same person on all the different treatments. So mixed design, kind of a combination of the two. But anyway, so let's just say we've got a within subjects. Okay. Independent variable, let's just say we've got one. Dependent, let's say we've got 3 or more. Dependent variable, we pretty much deal with continuous data. And do you consider many dependent variables jointly? Sure. So what we've got is a one-way repeated measures ANOVA. So this one is, because I clicked that it was continuous, and that last one that actually threw us into a different test. But, so anyway, that can be very helpful if you're not quite sure what statistics to run. So then we come up here, statistical tests. Go through all of these. They all have their uses, but So, so let's go over here let's just do a paired sample t-test. Click on it, and we get an introduction. So table of contents, here's all the stuff you get. Introduction, background, study design, flow charts, how to set up your data, assumptions. Unless you're doing hardcore statistics or you're publishing to a prestigious journal or you have a really, really picky professor or you're writing a dissertation, something like that, truthfully, most people kind of skip the assumptions. It's just that data needs to be arranged and collected, and it needs to represent itself in a certain way. So like normal data, your data needs to fall on the bell curve at the appropriate places. There shouldn't be outliers. So things like that, which we do anyway, but when you get into the assumptions, it gets just really gets complicated. So interpreting your results, let's just go here, getting started. Next. Okay, so here it's telling us that we have the mean average. N is the number of cases, standard deviation, standard error. So if you're going to write those out, you write it out, or it gives you an APA form. Okay, so general would be data are mean. So like it says, 11.3 plus or minus 7.4 kilometers, as opposed to carbohydrate drink only 11.167 and plus or minus. Okay, so that's only telling us what we found. That's the descriptive data for this research. It's not telling us if whatever we did was different. So now we come down and we do our t-test. So here's our t-score right here, degrees of freedom, our significance. So they're showing a significance of 0.000 something. So this means that our protein versus carb, I guess, is our comparison. Carb, protein minus carb. But they're statistically different, whatever it is. So, and the mean, so the mean we're getting here in this pair is the difference between the two groups. Okay. So carbohydrate protein drink elicited a mean increase of 0.136. That's our mean difference. 95% confidence interval. Our confidence interval, so basically what this is showing you is that's where 95% of your bell curve falls. 95% of your data falls between those 2 points. Okay. Then we come down and there's that. Let's go on to the next page. So here's actually how you write the t-test. Okay, gives you some details, but so APA. Carbohydrate protein drink elicited a statistically significant increase in distance run in 2 hours compared to a carbohydrate-only drink. So our T, this is degrees of freedom, 19. So if you go back up here, there's our degrees of freedom. So it's T brackets 19 equals our T score, which is this 6.352, and comma, then P less than 0.001. Okay, so that's how you write out a t-test. And kind of regardless of what type of t-test you're doing, they're all about the same there. And then again, it gives you some more details. And it gets into effect size, gets into a lot of stuff that it's not a statistics course, so we're not going into that. But so let's look at the one-way ANOVA. Okay, same thing, introduction, here's table of contents. You know, ANOVA is a little more complicated, so it's got a little more stuff, assumptions, again, how to set up the data, procedure, interpreting the results. You can see there's a lot of stuff to it. Reporting, so let's just go to, let's run through interpreting results. There's a lot of stuff, I'm going to ignore most of it. So here's our descriptives again. So sedentary, low, moderate, high, and total. Some variable called coping stress. Here's our means, how many people we had in each group, standard deviations, tells you what they're all about. Here's a graph that kind of describes it. Here's how they would write it up. The ability to cope with workplace-related stress increased from sedentary, n equals 7, that's the sample size, comma, 4.2, that's the average, plus or minus 0.8, that's standard deviation, to low, 5.9, to moderate, 7.1, to high, 7.5, in those orders. Okay, so those are, again, the descriptive data. It's just the means and standard deviations. Again, it does not tell us if the groups are different. Remember that. Okay, homogeneity, these are some of the assumptions, decision time. Okay. So I'm actually going to go to this branch 1. It gives you different options. So here's our ANOVA table. So between groups, coping stress, degrees of freedom 3, F score 8.3, which is pretty high, significance 0.000. So we know there's a difference between the 4 different groups. But again, it doesn't tell us what. So this is where we have to do and this is how you'd write that up. Ability to cope with workplace-related stress was statistically significantly different, so mouthful, for different levels of physical activity. F score, so these are your degrees of freedom. So 3 is between the groups, because you had 4 groups, so it's n minus 1. That's how they get the 3. And then total is, or within groups, 27. So 3 and 27, they put those. So if you were going to actually, the reason for that is, if you remember back to stats, when you looked up a z-score, there was a table and you needed degrees of freedom. This is degrees of freedom for looking up an F score. Okay. This is the score they got, and if you actually looked it up on an F table, you could use these to see what number you needed to achieve to get significance, which I would guess is lower than that. And our P is 0.0005. So they went out a digit. And again, they're showing you what I just told you right there. So it's very good. It's very detailed. Okay. If your one-way ANOVA is statistically significant, you can investigate further with a 2-key post hoc. So that's what we want to do. So I'm just going to do 2-key. Okay. So here we go. Here's our samples. Here's our multiple comparisons. So we're comparing sedentary. So this would be like what I showed you in class in Excel, where you'd have to do multiple t-tests to compare the groups. This is doing it all in one calculation, so you actually conserve variance, which doesn't violate assumptions, which multiple t-tests do violate the assumptions. So that's why why statistically they're basically illegal, and you just shouldn't do it. So sedentary versus low, 0.09. Okay, so sedentary and low groups are not different. Sedentary versus moderate, 0.02. They are different. Sedentary versus high, 0.01. They are different. Okay. Low versus sedentary, we already got that one. Not different. Low versus moderate, not different. And low versus high, not different. So far, sedentary versus moderate and higher are only differences. So now moderate, we've already done this one versus sedentary. We know that's different. Moderate versus low, not different. Moderate versus high, not different. High versus sedentary, different. High versus low, not different. High versus moderate, not different. Okay. So they go down here and then they're marking which ones are, which ones aren't. They give you a little more detail, telling you what it all means. Okay. So if you're writing up each one, here's your examples. Not statistically significant. Here, high versus sedentary. So there was an increase in the score from 4.2 plus or minus 0.8 sedentary group to 7.5 plus or minus 1.2 in the high performing group. Increase of 3.4. That's the mean difference here. Confidence interval, that's this, which was statistically significant, p equals 0.001. Okay. So that's, and again, it goes down and it gets into more and more and more stuff. But that's the basic is when you're writing up the data, you want these. At very least, you want a comparison table. Okay. Putting a comparison table and putting all of these written out just kind of depends. This is actually more what you would put in your abstract. Some of you didn't put much in your abstracts, and I maybe made a comment that you should briefly state what your statistics are. And this would basically be a brief summary of what your statistics are. Okay, so other than that, I think that's about it. And you can also go to Google and let's see, documenting statistics in a report. And good on Google. Just click on the first one that comes up. PDF file from University of Washington, I think it was. Psychology department. And so APA format. Yep, here you go. Significant correlations, significant single t-test, t-test for dependent groups, t-test independent groups, F-score in a one-way ANOVA, factorial ANOVA, chi-squared tests. So that's actually a good, it's basically the same stuff. There's really very little variation in how you report these. Some journals have their own way of doing it, but otherwise it's pretty much the same stuff. So hopefully that's helpful. Let me know, and I'll see you guys again on Thursday. Stop sharing, and I think that's it. Stop recording.